Hi, I'm Cawood. I'm here to briefly introduce our new Tessa technology, which is a revolutionary way in which to manufacture AAV. So Tessa stands for tetracycline-enabled self-silencing adenovirus. It's a modified adenoviral vector that allows you to manufacture AAV entirely free of plasmids. Yeah, so most AAV at the moment is manufactured using plasmids, but actually in nature, AAV lives in partnership with adenovirus. And because of that, we felt that if we could harness the potential of adenovirus to produce higher amounts of AAV and of a better quality, that we would be able to use that instead of plasmids as a new way to manufacture AAV. So in nature, adenovirus has two phases to its life cycle. Of course, as humans, we like to just split the life cycle into those phases, but actually from a technology engineering perspective, it was very, very helpful. So the adenovirus life cycle has an early phase and a late phase. The early phase is required for both AAV and also for adenovirus, but the late phase is actually only really required for adenovirus. So if you could silence that part of the life cycle, but still have the early part active, you could use an adenovirus to go into a cell to provide all the help that the AAV needs, and then not engage the late part of the life cycle and therefore not produce adenovirus coming back out of the cell. So you would have a very clean way of manufacturing AAV. So there was really two parts to the way in which we managed to control the adenoviral life cycle using Tessa technology. The first is that the late part of the adenovirus life cycle is entirely driven by a single DNA promoter, and that promoter has very rarely been modified in the past. So we've actually been able to modify that promoter to introduce a repressor binding site so that we're able to then repress all of the late genes of the adenovirus life cycle. Simultaneously, we then built the repressor that binds to that site into the adenovirus itself. And what that means is that the more the virus replicates and the more it tries to express its late genes, the more it actually prevents the expression of those genes. So we get a very nice negative feedback loop built into the virus, which tightly controls the late phase of the adenovirus. When you want to grow more Tessa, it depends on the repressor that you're using, but the repressor that we're using is the TET-R repressor. And so to grow the adenovirus and to engage the life cycle, so the adenovirus essentially becomes wild type, we simply add doxycycline to the culture media. So in order to use the Tessa technology to manufacture AAV, ultimately we want to be able to introduce the AAV components as well. The adenovirus, the Tessa adenovirus, could just be used as a helper virus, but it would be much more efficient if we could put those components into the virus itself or into the adenoviral vector. So that's been very challenging for many years. People have tried to encode both rep and cap within the Tessa virus, within an adenoviral vector before. Generally, both have been found to be very toxic to the adenovirus. So we underwent a number of engineering steps. We tried a lot of things that didn't work, and ultimately we ended up with some configurations that work really well. So now actually we're in a position where we can take the Tessa virus and encode both rep, cap, and the AAV genome within these Tessa vectors, which means we have an entirely scalable and completely plasmid-free process for manufacturing AAV. So because adenovirus is part of the AAV life cycle in nature, you would expect that the AAV quality and the amount of particles that you would be able to produce using this platform would be higher than perhaps using plasmid transfection. Certainly that is the case. I think it's also important to highlight that when you're transfecting DNA into cells, you are limited in a number of ways. Firstly, those reagents are very expensive. Secondly, you're limited by cell density. And thirdly, the process is not particularly robust. Tessa overcomes all of those challenges because you can essentially just add the virus to the cell culture media, it infects the cells in a very uniform way at higher cell densities, and it means you can really transform the amount of AAV that is produced in your bioreactor in comparison to a plasmid-based process, whilst also being of a higher quality and also of a higher yield generally. Ultimately, we think that the use of Tessa can significantly reduce the costs of manufacturing AAV. The number of input reagents is significantly lower, the efficiency with which they're delivered to the cells is significantly higher, and the productivity of the system is significantly higher as well. So if you can take a single bioreactor and produce all of a sudden 5 to 10 times more material from it, we of course hope that that will significantly reduce the costs of these very expensive but fundamentally life-changing therapeutics. So right now, we're in the process of transitioning the Tessa technology into a GMP environment. We're initially starting by developing Tessa materials for the manufacture of AAV6 and AAV8. At the Phacilitate meeting at the Advanced Therapies week in January 2022, we'll also be presenting all of the most recent data and where we are with our current progress and where that GMP transition is in terms of its development. But of course, if you want to learn more now, you can also contact our business development team on business@oxgene.com.